A rational number is a number that is written as a fraction. A rational function is a function that looks like it's in the form of a fraction. Hello friends, today we're talking about rational functions. And one of the things that you have to be able to do with rational functions is how to find domain and range, how to figure out whether it has a removable point of discontinuity, which is basically a hole. You have to be able to decipher whether it has a vertical asymptote, horizontal asymptote. And so what I want to do right now is give you a general overview of asymptotes and the behavior of these types of graphs, and then in another follow-up video I'll tell you how you can find the equations for the vertical asymptotes, horizontal asymptotes, and even slant asymptotes. So on your screen right now you have two rational functions. Notice they both look like fractions. You have a numerator and you have a denominator. If you take a look at the graphs themselves, you're going to notice some very special characteristics. These graphs are asymptotic. An asymptote is basically a line that the graph approaches but never touches or crosses. We can have vertical asymptotes and we can have horizontal asymptotes. If you look at this graph right here on the top right, you can see this arrow would continue all the way up towards positive infinity. And then here it's going to continue and continue and continue. But because there are both horizontal and vertical asymptotes on these graphs, then the graph is never going to cross or touch those vertical or horizontal asymptotes. So right now we say that we have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. And obviously I can tell by looking at the graph. But there is a way for you to tell by looking at the equation. If you take a look at this equation, one of the ways that you're going to be able to determine the vertical asymptote is to set the denominator equal to 0. Now, division by 0 is mathematically impossible. So in a fraction, the denominator can never equal 0. If we look at this function, f of x equals 1 over x, what would make my denominator 0? 0. So therefore, if I set the denominator equal to 0, that is going to tell me that I have a vertical asymptote at x is equal to 0. To find the horizontal asymptote, and I promise you that I'm going to do a video just on how to find the equation of the horizontal asymptote, you need to compare the degrees. The degree of a function is the highest power. So you're comparing the degree of the numerator to the degree of the denominator. The degree of the numerator will either be bigger than the one for the denominator, smaller than the one for the denominator, or exactly the same as the degree of the denominator. In this particular case, I see the equation f of x equals 1 over x right here. At the numerator, I don't even have an x. If I had to attach an x to the numerator, it would be x to the 0 power. And the reason is, I don't know if you remember, but anything to the 0 power is just equal to 1. So in this case, I'm not changing the value of that number, I'm just changing the way it looks. Then here in the denominator, I do see an x. When you see an x by itself, that degree is 1. So I'm going to go ahead now and try to determine what is the horizontal asymptote. And again, what I'm going to do is compare the degree of the numerator to the degree of the denominator. So in this particular case, the degree of the numerator is 0, the degree of the denominator is 1. That means top is smaller, the degree of the numerator is less than the degree of the denominator. Therefore, automatically, when the top is smaller, y is equal to 0. Another thing that I want to talk about in terms of rational functions is what we call the end behavior. What is happening to the arrows at the end? Well, as I move to the right-hand side, as x approaches infinity, that means the right-hand side, notice that the graph is just going to continue closer and closer and closer to 0. So the function approaches 0. As I move towards negative infinity, then notice here that as x approaches negative infinity, my graph, my function, also approaches 0. That is because there is a horizontal asymptote at 0. If we talk about the local behavior is what is happening towards the center of this graph. Notice that my graph gets closer and closer and closer to this vertical asymptote of 0. So as x approaches 0 from the right-hand side, that's what that plus sign says. as x approaches 0 from the right-hand side, then the function is going to approach positive infinity. And as I come from the left-hand side towards 0, notice the graph is going to continue towards negative infinity. So as x approaches 0 from the left, that's what that minus at the top right corner means, then the function is going to approach negative infinity. If you're lost with this whole idea of end behavior, local behavior, let me know and I can go ahead and do another video where I kind of specify about it. What I want you to familiarize yourself with in this video is simply just some of these properties dealing with these rational functions. If we take a look at the one on the right hand side, notice that they are also asymptotic. I have 0 as my vertical asymptote and I have 0 as my horizontal asymptote. So the vertical asymptote is still x equals 0 and the horizontal asymptote is y equals 0. But now these arrows towards the middle, the local behavior, they're both pointing towards positive infinity. And the reason is because the equation is 1 over x squared. And that x squared means that whatever number of x is negative, the answer is still going to be positive. That is going to become important eventually down the line when you are given a graph, and it is going to be your responsibility to come up with the equation of that function. So again, if you notice that these arrows are going to be going in opposite directions, the way it's happening here in the first graph, where this arrow close to the vertical asymptote is going in opposite directions, then you know that it's not going to be over x squared. It's just the reciprocal function, but not the reciprocal squared function. If in fact the arrows are going to be going in the same direction around that vertical asymptote, that tells me that in fact I do have a reciprocal squared situation because both arrows are pointing in the same direction. Take a look at this graph. Something interesting about rational functions is that it's possible that they have what's called a removable point of discontinuity. And if you notice on your screen, this right here is a removable point of discontinuity, aka a hole in the graph. So basically, we have these holes in the graph, and the way you identify a hole in the graph algebraically when you are given an equation is that you're going to have to factor both the numerator and denominator. If factors are found that are alike top to bottom and you can cancel them, then that's when you're going to end up with a hole, which is, like I said, a removable point of discontinuity. Now, there's also here a vertical asymptote at x equals 3. And one of the things that you need to know is that an asymptote is a non-removable point of discontinuity. If I were to fill in this hole right here and I wouldn't have it anymore, this graph on the left-hand side would be continuous. But if I were to go ahead and get rid of and just delete this red dotted line, which is the vertical asymptote, these two parts of the graph that you see, they would never cross, okay? So this part of the graph and this part of the graph are still not continuous. And so an asymptote is called a non-removable point of discontinuity. Even if you remove it, the graph is still discontinuous. But a removable point of discontinuity means that if I were to get rid of that hole, then my graph would continue to be continuous at those points. If you take a look at this graph, there's a few things that you need to notice. Number one, there are two vertical asymptotes in this graph. It is possible for us to have more than one vertical asymptote. The second thing is, notice that we said that asymptotes are lines that the graph never crosses and touches. And yet we have a rule breaker right here in the middle. This graph completely crosses through that horizontal asymptote. That is something that happens. And it usually happens in between two vertical asymptotes. So when you are asked to graph these yourselves, you're going to have to pick a lot of points in between two vertical asymptotes to determine what is going to be the behavior of the graph at that point. Is the graph going to curve and not pass the horizontal asymptote, or is the graph going to be a rule breaker like this one is, where it does cross that horizontal asymptote? And then you might also be wondering, well, why does it still considered to have a horizontal asymptote if in fact it's crossing it? Doesn't that basically defy what the definition of an asymptote is? Well, the answer is because at the end, the graph does behave asymptotic. As x approaches positive infinity, then the function is approaching 0. So as x approaches positive infinity, the function approaches 0. On the left-hand side, same thing. As the graph approaches, as x approaches negative infinity, then the function approaches 0. Therefore, the behavior is still asymptotic, but in the center, the graph does cross, and that can happen. So this video is just to give you an introduction to things to come in terms of rational functions. I hope you found this video helpful. Remember to subscribe to my channel for more help with math so that you can say, yes, I can do math with confidence. Until next time, thanks for watching.